Alright folks, we wanted to start getting into the optimizations. Apologies in advance, this might turn into one of the longer videos, we'll see how this goes. But we want to look at local optimizations this time around. So this is optimizations that are performed just on one of the small basic sequential blocks. So we've got some block of instructions with no, it's sort of the one entry point, the one exit point. Anytime you get into the block, you do every instruction in the block in that order. So that means that you've got much simpler analysis than with the more complex structures. There's no branching taking place, right? There's no worrying about anything other than the instructions right at hand. Now, that does make the analysis simpler, but it means there are fewer optimizations to take advantage of because you don't have information about things that are happening outside the immediate block. So you've only got this narrow context, but there are quite a number of things that you can do in terms of optimizations there before we move on to look at optimizations in the bigger scope. So we can go through and, if we've got some expression that we're looking at and it's got a bunch of constants in it, we can evaluate those constant expressions and replace them with a single constant value, so that'll improve runtime. We can go through, and if we see computations that make use of a value that we computed earlier, again, we can store the earlier computed value in a temporary variable and make use of that rather than recomputing it. So again, we can simplify things. We can try and simplify expressions by applying identities and by taking advantage of sort of commutative rules and associative rules for operators. So, if you've got something that's multiplied by 0, you can replace it with just the constant 0. If you've got something that's, bit shifted by 0, you can substitute just the ordinary value. Again, there are a bunch of identities we can apply to try and simplify things, rewrite the expressions so that they are in a simpler form. And we're also going to try and rewrite the expressions so that if the processor we're running on actually supports some parallelization, we've got an implementation that will work with that. So these are some of the goals, and we'll tackle all of this in examples over the next, half an hour. So one of the things that we're going to take advantage of is the idea of local value renumbering. So the notion is that we're going to associate a unique integer ID with each of the different values that we compute in the block. And then, again, like we've done with some other algorithms in the past, where when we want to refer to that value, we've got this number and we can just say, I want to use the number that's in ID whatever. And we're going to generate names eventually to go along with these numbers and say, okay, well, I want to use the value that's stored here when it comes to generating the actual code. And again, this gives us a way to refer to previously computed values and use them over rather than recomputing them. Now, as far as expressions go, if I can prove to myself that two different expressions have the same result, right, provably equal values, then I can go through and say, okay, well, those two expressions can be treated as equivalent, and I can give them the same value number. So, if I had an expression that was 3 times a, and I had another one that was a times 3, then I can go through and say, okay, well, those are going to have equivalent values. I can use them interchangeably. So whichever one I computed first, I can reuse that value for the second. So we'll take advantage of some ideas along those lines, but we've got to make sure that the expressions do actually match. The values are correct. And what we're going to do is go through a whole series of statements. So let's assume our block is a bunch of statements, and for the moment we're just going to simplify and say all our operators are binary operators. So we'll say we've got statements of the form, some variable is assigned some value, and then your operator and some other value. And again, these values are going to be either literals or variables. Right? So just a whole bunch of really simple expressions, and we're going to go through and try and associate numeric IDs with each of the different variables, and with, effectively, since we're going to have to compute the result of an expression, with the result of, we'll have to associate value with the destination variable. So if this L op R winds up computing some new value, and we store that in T, then T's got a value number that reflects that. So that's more or less where we're trying to go, and we'll come up with an algorithm to do that, and then we'll take a look at how we can use that to our advantage. So again, we're going to assume that we've got this block that's a whole bunch of statements, t is equal to L op R, and whatever, L and R might be literals or they might be variables. So what we'll do is keep track of a table of the local value numbers that we've seen so far, right? So we'll just keep track of all these things. Every value is going to have an ID associated with it, and we'll see which ones we can reuse as we go along. So if we've got n statements, right, n operations of this form, then we'll go through each of them in sequence. And the first thing we'll do is look up the value numbers for the two operands. Right, these have got to be things that we've computed earlier, otherwise it doesn't make sense, or they've got to be variables that were defined prior to the block. So we've got these values available. So on the first, if it's a variable and this is the first time it's being seen in the block, then we're going to assume it was defined previously, and we'll give it, we'll generate a new value number for that one. So if this is the very first statement in the block, then L is going to get, value number 0, and R is going to get value number 1. And when we compute that result, T is going to get value number 2. So we'll generate new numbers as we go. And again, first time we see a variable or a literal, we'll associate a new number with it. And we'll go through, compute a result, associate the value for that, or a number with the value for that on the left-hand side. Now, if this operation is one that we've seen before, then we can reuse the value that came from that. So if I had something like, x is assigned a plus b, and later on I see another a plus b, as long as they haven't changed in the interim, which will be reflected by our value numbers, if I see a plus b again, then I can just reuse that computation. So that means that we're going to have to store information about these expressions in the table. So we'll have to have something that identifies which expression we're talking about and the value number that we've associated with it. So when we're going through this algorithm, and again we'll see in just a moment where we wind up doing the inserts of information about an expression, if the expression is one that we've already seen, then instead of saying, my left-hand variable is assigned whatever this expression is, I'm going to rewrite that instruction to be my left-hand variable is assigned and whatever the right-hand value was from that previous one. Right? So sometime previous, if I said a is assigned b plus c, then here I'm going to say, oh, well, my new variable, it can be assigned a. So I can do this rewriting as we go if it's an expression that I've seen before. If it's not one I've seen before, then I'm going to need a new local value number, and so that I can associate with this value. We'll insert this expression into the table so that now I've seen this new expression. Here's the value number associated with it, and we'll record that value along with t in our table as well. Right? So now I've got a new value associated with the expression and with the t, and we're good to go. Right? So this is going to go through adding new variables as we go. It's going to identify variables we've seen for the first time, right? Everything gets its own value number. And again, anytime we see something that we've already used before, we can look it up in the table, say, I've seen that before, grab its number and reuse that. So let's play with a bit of an example here so this makes more sense. So we'll take a little chunk of code, and I'm going to have a chunk of code where we reuse a couple of values, but for one limit, the data is going to change. So we'll say w is assigned x minus y, x is assigned, w plus z, y is assigned x minus y. So now y is changing, and z is assigned w plus z. So w and z don't change after that initial statement here. So we can go ahead and quite happily reuse the values we've got for w and z. Actually, I think I've got a glitch it. No, we'll get there in a sec. So we want to be able to reuse these. I was thinking that we don't want to reuse the x minus y because y is being updated, but y is actually getting updated as a result of the expression. A little gray. All right. So in theory, the value that we're computing on the right-hand side here is correct until we compute it and assign it to y. However, Let's see. So in terms of assigning our value numbers, right, we're going to go through. This is the first time we've seen x, so we'll give it a value number of 0. This is the first time we've seen y, so we'll give it a value number of 1. This is the first time we've seen the expression x minus y, and so we'll store, x minus y as an expression in our table and give it a new value number, so let's call that one 2, and that's going to be the same value as associated with the left-hand side w. And then we continue going through. Our next expression, we're seeing w plus z. Well, w we just set. It's got value number 2. Z's a new variable. We'll give it variable or value number 3. X is going to be the result of a new combination or new computation, so we'll give it value 4, and we just keep on going. Right? We're going to use the x that we just had. We're going to use our old y, but we're going to assign a new value to y. So now we've got a new value in y. Right? It's not the same value as our old one. And again, we wind up using our same w plus z. And again, when we look up this w plus z in our table, we're going to see it's the same w plus z that we saw earlier. Right? The value numbers are the same. So we're going to find this and say, well, what was that? That had the value 4 associated with it, the value number 4 associated with it. So that's the same one we can use here. Right? So we can give z this value number 4. And now we actually can tell that x and z have the same value stored in them. However, we can go through and, again, associate value numbers with the things that we're computing as we go. We can reuse things when we see them. Right? When I hit this point, when I'm doing the rewrite on my code later on, when I go to try and rewrite this stuff, where I see that we're reusing a previously computed value, I can just substitute, instead of writing again z is assigned w plus z, I can just say z is assigned x, right? Because I know that those values are the same. So I can start rewriting my code based on this to try and create simpler, shorter code. All right, now, we have to go through and, like I said, store information about these expressions in the table so that I can recognize when I've seen an expression before. So one of the ways that we can do that is just to create a hash function and have a hash table. So with each operand, operator, operand combination, so each left operator, right combination, we'll apply the hash function to those three things and have it tell me where in the hash table this thing is being stored. And we'll need some collision resolution mechanism, but we'll ignore the gory details of hash tables for the time being and say, okay, we'll hash this to some unique entry in the hash table, and then we can, if it's the first time that we've seen this expression, we'll insert it at the hash table at that location. If there's already if we've seen that expression previously, then we can, great, I've got that expression already. I can look up its value number from the hash table. Now, having said that, we can start making some tweaks, start taking advantage of our hash table or our hash function to improve things for us a little bit. When I'm going through, if I see, x is assigned y plus z, really that's the same thing in terms of a value as saying x is assigned z plus y. Right? If addition is commutative, then it doesn't really matter which way we have this written. It would be nice if I could recognize that these two things are supposed to be the same value, right? That I don't really care what order they wrote the operands in. So maybe I tweak my hash function so that for operators like addition, L plus R and R plus L hash to the same location in the table. That way when I do either one, it says, oh yeah, here it is. So this way we can start making some improvements that immediately allow us to make some simplifications that we couldn't make previously. Right? So we're already making progress in terms of how we can improve this stuff. Now, we can take advantage of some other ideas. As we're going through, we can also start saying, well, what if I see a constant expression, right, where both the operands on the right-hand side are constants? Then, instead of actually writing that into the code as having the code say x is assigned 3 plus 5, what I could do is say, well, let's just evaluate that now So we'll figure out now that that's 8. And we can rewrite as x is assigned 8. And we can also make a note in our table, so new field in our hash table, to keep track of the fact that x is now a constant. So later on, if I see something like 12 plus x as a later instruction, I can go, oh, that's a constant operation too. And I can fold that one in and replace that with a 20. And so we can collapse a lot of these constant expressions. Later on, we'll take a look at the idea that, well, maybe if I've got a whole bunch of constants scattered through an expression, you know, if I got 3 plus y plus 7 plus a, then I can go through and group all of those constants together, again, assuming that we've got commutative operations, then we can, and associative and whatnot, then we can go through and group them together and perform the constant time addition and get rid of all of them at once into a single value. So there are things that we can take advantage of as we're going through this. So constant folding is one of the things that we'll take a look at. Identities as well, right? There are a lot of simplifications we might be able to apply based on just the Boolean rules or the math rules, the identities that are floating around that we know we can take advantage of. You know, if I add 0 to something, I just get my original number back. So if I see that in an expression, then I'm just going to say, oh, well, you know, I'm going to simplify the expression and just use x. You know, if I multiply something by 1, or if I multiply something by 0, or if I raise something to the power of 1 or something to the power of 0, again, I know what the result is going to be, and I can simplify it. I don't have to include the entire original expression in my generated code. I can just use the simplified version. You know, if I bit shift something left or right by 0, then I'm just getting my value back. Bit shifts as well, if I multiply something by a power of 2, then I can replace that with a bit shift operation, which is going to be much more efficient. So I can start applying these identities as I'm going through renumbering things. And again, there are a slew of others and lots of special cases depending on your hardware that you can take advantage of. But it's all stuff to keep in mind, that you can get your compiler to go through and recognize this stuff. And now we've got a reasonable spot in our algorithm to try and tackle that. Now, we talked before about some of the issues with naming and how it complicates our life. That's going to crop up here again. So we talked about the sort of single static assignment idea, where we always make sure we use a new variable name on the left-hand side of an assignment statement. Well, here's, again, an example of where that crops up. If we're going through using the approach that we just took, this sort of value numbering system, where I've got, you know, v is assigned w plus x and y is assigned w plus x, then for this second one I can go, oh, I can reuse this. I can just rewrite it as y is assigned v. Then I change the value of v, and later on I do something like, you know, z is assigned w plus x again. Well, I've lost my ability to reuse v. You know, maybe I could recognize that I've got y available back here in this particular case, but I've lost my ability to reuse v simply because I overwrote a value I'd computed earlier. So we could at this point go through and say, well, when I overwrite a number, can I go back through it? Can I go back through my hash table and update the entries to reflect this sort of changed entry? Or I can make my life a lot simpler at this end and just say, you know what? Use the unique naming when you create names, when you generate your names at that intermediate representation, and we don't have this problem, right? We'd have some new temporary variable name here, and that would be getting used instead of v in our subsequent expressions, and we could simply reuse v here. So again, naming, if we're using unique names on the left-hand side, life does get easier. Pointers and ambiguity, again, we've mentioned this a couple of times now, but they do create problems for us. You know, if I've got a block of code like this where I'm saying, okay, A is assigned B plus C, and then I'm using a pointer and assigning a value of 5 to somewhere in memory, I don't know if any of these things have changed. I don't know if A or B or C have been wiped out by this. And so any place after that where I'm using these things, I can't trust that those values have changed. So I have to think of A as having a new value after this point, and B as having a new value after this point, and C as having a new value after this point, because I can't trust the old values, right? I can't trust that they're not 5. So as far as our algorithms are concerned, they have to treat it as if all three of them have changed. In reality, we know at most one of them can have changed, and probably none of them did, but our compiler can't trust that. It can't take that chance. So it has to act as though all three have changed. All right. The next stretch I want to get into is an interesting one, and it revolves around the idea that lots of processors now support, have hardware on board for things like multiple adders. So the processor is a little more advanced now, and you can do things like carry out multiple arithmetic operations in a single step, right? In a single cycle, a single instruction cycle, you can have multiple instructions, multiple additions or subtractions or whatever it might be taking place. So that means that if I've got an expression with a bunch of additions in it, for instance, I can throw one addition into one of those and another addition into the other one and have them taking place in parallel. That's great if I can evaluate my expressions in a way that supports that. So if I had an expression like w plus x plus y plus d, then we went through, if we take our standard sort of math rules, we're doing this left to right, so I'd add w and x together, and then add the result of that with y, and then add the result of that to d. And so if I was writing this out as our kind of assembly language, we'd have these steps where, t1 is assigned w plus x, t2 is assigned t1 plus y, t3 is assigned, t2 plus d. And so you're still stuck with this 3 instruction cycles because there's no way to parallel, there's no parallelization there, where each operation depends on the results of the previous one. But if we wanted to, if we recognize that we can rearrange these without changing the value, then I could reorder the plus operations. Then I could add w and x, for instance, in one of our adders and y plus d in the other one, and then add the two results together. And so you've got the two first computations taking place together, and then the one additional operation afterwards. So now we've got 2 instruction cycles used rather than 3 instruction cycles. And again, the idea that if we've got a lot of operations going on, maybe we can parallelize a lot of them and make a significant speed up. Now, I mean, the best you can get is twice the speed that you originally had, but still, that's a decent improvement. So, rewriting and parallelizing. Lots of things that we want to be able to do here. Now, for the moment, to keep life sort of manageable, we're going to assume that in the piece of an expression that I'm working on, we've got a single type of operator that we're using a whole bunch of times, like a whole bunch of additions or a whole bunch of multiplications, and that it's both commutative and associative. If that's the case, then I can take my expression and reorder those things in any order I like. Which means that, if we're thinking of the abstract syntax tree to represent this, I can build the tree in any structure that I like to try and get the best parallelization opportunities. So again, the default handling for this would be the same as we just discussed, where, we go compute the sum of the first 2 elements, store that in a temporary value somewhere, then add the next one and store that in a temp, and add the next one and store that in a temp, and you've got this inherently sequential process. If I can juggle these things around, then for one thing I can realize that I can add this 3, 9, and 200 together right at the beginning and get 212 and chop out sort of 2 operations there. And I can restructure it so that I do some of these things in parallel. So I do my x plus y, for instance, in parallel with my z plus 212, and then I've just got this one extra operation at the end. So we've gone from sort of 5 cycles to go through this to 2. And again, it provides us with an opportunity for improvement. And even if we didn't have the extra adder available, then we've still managed, by rearranging this, to fold those constants together and get improvement there. All right. I mentioned this idea that we wanted to kind of think of our expression as being this abstract syntax tree. And what we're trying to do is, the nodes are the operations and the leaves are the values that we're operating on. What we want to try and do is to balance the tree as much as possible, try and reduce the tree height as much as possible, because that means that we're kind of spreading the tree out and we've got as many things as possible happening in parallel with one another. And that does give us this good representation that will allow us to parallelize things well. So again, for simplicity's sake for now, we'll just assume that, again, all of our operations are this binary form where we've got, some variable is assigned some variable or value, an operator, and some variable or value. So these will just be either vars or constants, essentially. And we'll just have a whole sequence of these, and what we'll try and do is build, we'll read this sequence of instructions, build our tree if you like, and rebuild it to be more efficient. Now, of course, this can't alter the observable values, right? We don't want this to actually change the result of the computation, just change the way in which we do the computation. We don't want this to be bigger than the original. We don't want this to take longer than we originally did. And we're not going to let it look outside the block that we've got. So we're just working within the set of instructions that we've got. When we get to the section on regional optimizations, then we'll have information about stuff that comes before and after the block. And in particular, when we get to the section on subroutine optimizations, there we'll have everything associated with a subroutine available to us. Other than global variables, but that's something we'll save for another day. So we're going to kind of build this dependency tree that shows us which values need which other values computed first. Then we'll try and rebalance it, again, to do things like constant folding and to structure it so that as much as possible is happening in parallel. Now, again, we can't rewrite an entire tree just at random if it's got a bunch of different types of operations in it. Right? We can't arbitrarily reorder subtractions or divisions. If we've got multiplications and additions mixed together, then we have to make sure that we've followed our precedence rules for which ones happen. So again, what we're going to try and do is restrict the rebalancing part to just those portions of a tree where we've got just one type of an operator and it's one of the commutative associative operators. So having identified the part of the tree that we can restructure, we'll find its root and we'll use that root as the point to start restructuring. So the preliminary stage in this would be going through our abstract syntax tree and identifying the roots of subtrees that were just additions and the roots of subtrees that were just multiplications, that kind of idea. So let's just say we've identified the roots of these trees, and we'll order them by the precedence of the operators. So we'll do multiplications first, obviously, and additions later. And what we'll do is, since we're going through processing, let's say, one of our addition subtrees, then we know that everything in this subtree is being added together. So all we really need to do is to come up with our list of things that are being added together, right? The names of the variables and the literals that are being added together, stick them in a big list, and then once we've got that big list, we can build a tree from that list that does things in an optimal structure, if you like. So we'll identify that once we've identified the trees, or the roots of these trees, we'll go through and build these lists. And once we've built the lists, we'll go through and rebuild the new trees. And from those trees, we can generate our resulting code, our rewritten code. So what we'll do is, as we're going through this process, we want to identify things that we need to compute before other things. So if I've got a constant, I can use it right away. So I'm going to give those constants a rank of 0. And the lower the rank, the earlier we want to process it. So constants get a rank of 0, variables will get a rank of 1, and then for all of the expressions, we're going to rank them based on the rank of their subtrees. So if I've got an expression that's the sum of two constants, it's going to get a rank of 0. If I've got an expression that's a variable plus a constant, it's going to get a rank of 1. If I've got an expression that's the sum of two variables, it gets a rank of 2. If it's an expression of, the sum of two subtrees, then it's going to get the sum of the two subtree ranks. And so what we'll get are ranks for things that are higher in the tree wind up getting a higher rank, which means we'll process them later. Right? This guarantees that the things that we can work with right away are at the front, and the things that have to wait until we've computed a bunch of other stuff are at the back. So this is going to be the notion of our ranking scheme as we go through this. So the algorithm itself, again, assuming that we've identified the roots of the subtrees that we're interested in, and we'll give the root nodes a rank of -1 initially just as a flag that we haven't processed them yet. And what we're going to do is for each of those subtrees, for each root node, we're going to call this balance routine. So the balance routine takes a tree node and tries to figure out what to do with the tree. So basically it's just going to take a look at that tree and say if it's something I haven't processed yet, so if its rank is still -1, then what I'm going to do is initialize the queue of things that are going to be added together or multiplied together for this subtree. Right? So again, we've just got this list of things that are going to get added together, or this list of things that are going to get multiplied together. So I'm just going to set up this queue to record the names of all of those things. I'm going to figure out what the rank of this tree is. Right? Again, we're representing this operation. I'm going to figure out what the rank of, this variable is for the left-hand side. Right? This is going to be if you like, the variable that's associated with the result of our subtree n. So what I want to do is go through and process, if I've got this operation that's, t is assigned, some left, an operator, and some right, then left could be a number, or it could be a variable, or it could be a subtree. Same thing with right. So what we'll do is figure out those first, and then assign a rank for my current node for my t here. So my resulting rank is going to be the result of, and I'm going to use this flatten routine to go through and process the left side and the right side. So flatten takes the node for the left side, or the node for the right side, and it takes the queue that we're supposed to be filling in, and it's going to go through and process the left side, sticking things in the queue as it finds them, or process the right side and stick things in the queue as it finds them, and then it's going to return the rank of the stuff that it processed. So once I've done that, once I've flattened those two sides, then I know that I've got my, and this should actually be t, I think. Then I'm going to say, okay, what I've got to do now is go through and from that list and the operator that I'm using, so addition for instance, I have to build my new tree. Right? And so this rebuild is actually, it's going to sort of implicitly build the tree. What it's going to do is spew out the code for this as it goes. So a lot of the interesting stuff is happening in Flatten. Again, it's being given the subtree that we're working on, or the node for the root of the subtree that we're working on, and it's given this queue that might already have stuff in it. We don't know. We don't care in Flatten. We're just going to be adding stuff to it. And it's going to return the rank of this subtree once it figures it out. So we've got this node, we've got this queue, and we're just going to look at what kind of data it is. If it's a constant, then I can just stick it in the queue and give it a rank of 0. If it's a variable, I can give it a rank of 1 and stick it in the queue. Otherwise, it's either the root of some other subtree that we've got to balance. So if it's a root of one of our other subtrees, so if it's one of those ones that we stuck in with a value of -1 so far, then we're going to have to say, okay, well, first I have to balance that and then add the result of that to my queue. So if this comes back and says, okay, well, the root of that wound up in, variables temp 77, then we're going to enqueue the temp 77. So we go through and balance the subtree, and then we can continue processing here. It gives us back the rank eventually, which we can give back. Otherwise, If it's not the root of a subtree, and it's not a constant, and it's not a variable, then it's just a regular old operator, one of the operators that we're interested in. So now I can go through and say, alrighty, that in turn is going to have left and right operators, so we'll call flatten on that on the left side and flatten on the right side, and that will take care of adding other things in. They give us back their ranks, and we're going to add those together and return those as our rank. Right, so flatten is just going through and figuring out all of the data values in the subtree, quitting at the places where it has to stop. All right, so we said that in our balance routine, after it's gone through and flattened the two sides, then we want to go through and rebuild. So we've got all of these values that are in the queue and the operator that we're supposed to be using to glue them all together, and whatever the name of our current node is, or current variable is. And so what we want to do is, as long as there's things still in there, now one of the things that we know is, since we're strictly using binary operands, is they're all getting stuck in pairs, but that's another story. But what we'll do is pull the next two arguments from our list, and we go through, grab one for the left, one from the right, remove them from the queue. If they're both constants, then we can do our constant folding here, right? We can add them together. If this is the last thing in the queue, right, if there's nothing else left, then those two are our result. So I can print out whatever my root name is and the result, and I can give 0 as the rank for this, right, because I've just computed a constant value. Otherwise, then I want to enqueue this thing with a rank of 0, right? I want to enqueue my constant because it's going to get used in a later computation, right? This is, if the queue isn't empty, then we're somewhere in the midst of this, and we've got a value that's got to be added to the other values that are out there someplace, or multiplied to, or whatever. So the other case, so this was the case where left and right are both constants. The other case is where at least one isn't. So we've got a constant and a variable, or a constant and a subtree, or two variables, or variable A, blah, 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 blah. So again, we have to think about what are the possible conditions. If this is the last thing in the queue, then we want this to go into whatever our node's name is, right? We want the variable for this to wind up being in our node's name. And otherwise, we want to go through and come up with a new name, a new variable name, a new temporary variable name for the destination to store this value in. And we're going to emit the code for this. So whatever name we came up with here, either the name for our root or the new name that we just created, we're going to say that is assigned, and whatever our two left and right values are, right? Those two values that we popped out here, we grabbed a left, we grabbed a right. So now we're saying, okay, well, the result is equal to, and whatever that left is, and our operator, and whatever our right is. And the rank is the sum of the two ranks for L and R. Right, so we can go through, and this is where we're actually spewing out the code for the current operation. Now, if the queue isn't empty yet, if there's still stuff to process, then the thing that we just computed here is actually buried in a subtree someplace, so it's going to get used by somebody else. So we have to put it back in the queue for whoever's using it, upstream, if you like. So our rebuild is going through, identifying when we should write out a new code statement saying, blah is assigned, blah plus blah, and when we should put things back in the queue to be processed later. Right, taking care of our constant folding as we go. So in terms of an example, so here we've got just a bunch of statements, and again, just to keep this simple, we're using all plus operations for the moment. So we've got 7 statements here. And we're reusing some of these variables. So, C is assigned A plus B, and later on we'll use C. And E is assigned B plus D, and later on we'll use E. So we'll go through, and we've got this sequence of statements. And if we think about what the tree representation is, just as is, sort of the abstract syntax tree for these, we're saying, well, A plus B is C, and then A plus C is F, and then 2 plus F is I, right? So these are the statements that we've got going on here. We've got our B and D is E, so our B and D, oops, I'm missing a connection there. So B, a dependency there. B and D are E. What else have we got floating on there? 2 and 5 is G. 3 and G is H. So on building up here. E and, oh my goodness, typos galore. E and H should be K. Sloppy, sloppy, sloppy. Okay, I will fix those. But, so this should be E and H or K. And I should make a note to fix that. And so what we'll do is we build this sort of syntax tree, and you can see that things really aren't ideal. There's a lot of things where if we were trying to parallelize this, we'd have stuff that was sitting idle. We've got tree heights that are probably larger than we need. We've got all of these different constants scattered around on in this subtree that we could theoretically group together if we restructured this. So actually, if we come back and think about this, if we're looking at our structure here, right, for I, we've got A and B and C, or pardon me, A and B and 2 are pretty much the only things that are getting added together, right? We're just finding a very convoluted way of doing this. And for K, we're adding together the values on the, I see what's going on here. This should be E plus D, and this should be our 3 plus G. Oh my goodness. I'm going to have to go through and restructure this one clearly. But again, the notion is we want to take our code, restructure it, rewrite it so that we get a more balanced tree, a better structure out of all of this. So if we try to apply our balance routines, oops, keep trying. Try and apply our balance routines, then what we want to do is identify the roots of the relevant trees in here, and the roots are essentially the two destinations, right? The I and the K, the top elements of these. So we want to start from those roots and work our way down, rebalancing as we go. So we'll look at the balance routines for I and K, right, our two final destinations. So if I is our 2 plus F, then we're calling flatten, balance is calling flatten on the 2 and the F. Right? 2 is a constant, gets a rank of 0, gets stuck in the queue of things to be added together. So the flatten of F, we've got to continue processing. The flatten of F, well, F is A plus C, so the flatten of F is calling flatten of A plus flatten of C. A is just a variable, so it gets a rank of 1 and gets included in the list of things that we're supposed to be adding together. C is one that we're going to have to flatten as well. So what was C? C was A plus B, so C calls flatten of A and flatten of B. Those are both just variables, so they each get a rank of 1 and get stuck in the queue of things to get printed out. And at that point, our queue is empty. Right? We've gone through, our queue is empty. We've hit the bottoms of our trees, the leaves of our trees. So now, our queue has got the things that we've queued up here. We've got the two A's that got queued up, the B, and our rebuild is being said, okay, for node I, here's the list of things that you have to add together. And so the rebuild is going to go through pulling out pairs, right? It pulls out that first pair and says, okay, we've got B plus A, and sticks the temp 1 back in the queue. And it pulls out the next two things, and it says, okay, so we've got A plus 2, and sticks that in temp 2, right? It's emitting the code for this, and sticking the temp 2 back in the queue. And then it pulls the temp 1 and temp 2 out of the queue, and says those are getting assigned to I because there's nothing left in the queue. So this actually goes through and restructures our tree implicitly, right, rebuilds our tree and generates the new substitute code. So now we've got these three operations that are used to compute I, right? temp1, temp2, and I, as opposed to what did we have going into I before? The A plus B, and then the addition of A to get F, and then the addition of that to get 2. So I guess we've gone from 4 instructions taking 3 cycles to 3 instructions taking 2 cycles. Right, so again, we've improved the tree that we're using for this computation process. And then if we were to take a similar approach to looking at balance of k, again, if we take a look at k, it was E plus F. So we've got flatten of E plus flatten of, or pardon me, E and H. Is that right? That was the mistake that I made earlier. That should have been E plus H. That's right. So we've got flatten of E plus flatten of H, and our flatten of E is going to go back and call flatten of B and flatten of D, which were both variables. They both get rank 1, and they get stuck in the queue of things to be processed. Right? H goes through its tree and says, okay, I'm supposed to be adding together 3 and G. 3 is the constant, queues that up. G is a subtree, so we look at that. G was the subtree that was adding together 2 and 5, so calls flatten on those. Those were both constants, so they each get a rank of 0 and get stuck in the list. And now what we wind up with is our enqueued list of the 5, the 2, and the 3, and the D and the B. As it's going through seeing these things, right, it pulls those 2 out and says, that's a constant expression, that's just 7, I can stick that back in. And then it pulls the 7 and the 3 and looks at that and says, that's a 10, I can stick that back in. And then pulls the 10 and the D, says, oh, okay, I better emit code for that. So now I've got, I generate a new temporary variable. Our temp3 is 10 plus D, and puts the temp3 back in there. We go back and look at this, and what we've got left is B and the temp3. So we add those 2 together, right? Emit the code for that, assign it to our root, and we're done. So this time we're down to 2 instructions, in this case taking 2 cycles, as opposed to however many instructions we had for computing k before. I guess we must have had 4 instructions for computing k. The E, the G, the H, and the K taking 3 cycles. So again, we've managed to shave a cycle off, we've managed to shave some instructions off, and we've got a better expression for our tree. And this is the goal of this kind of renumbering, restructuring process, is to try and come up with ways where we can identify things that we can reuse, and identify things that we can simplify, and identify things that we can reorder. Right? You can see how in the algorithm we could also quite happily go through and say, well, maybe in here we have additional cases where we look at simplifying the expressions as well. Right? Take a look at opportunities to try and simplify the expression that we're working with. But we will leave that for another day. So, lots of fun. Sorry this was a longer one than most, but again, we've got a lot of the ideas and concepts that we'll use in sort of future techniques to carry out other forms of operations. We'll expand this value numbering idea to areas bigger than just a single block in our next section as well. All right, I will leave that there.